All right, let's get started. Hopefully you guys have figured out GitHub and your labs are going well. Let me know if there's any questions with that. So in lecture, we've been working on multiple linear regression. This is where we predict a scalar target y from several features x1 through xd. And the first thing we did was we derived this expression for the least squares versions of the trainable parameters beta 0 through beta d. And this expression uses this A matrix, which contains the training feature data as well as a column of ones, and also the training targets. But then we said that this expression may not be very insightful because of the complexities of how A is being used and because of this column of ones that we added. So then the next thing we did was we looked at the problem a slightly different way, where we took out the beta 0 term and treated that differently from all the slope terms, which we called beta 1 through d. And then we defined some new statistics. These were extensions of the covariance and mean covariance, cross covariance statistics from the last unit, where we extended them to multiple features. And with these new statistics, we were able to get expressions, here they are, expressions for the least squares solution that look a lot like the expressions that we derived in the last unit, which involve these statistics. So capital SXX is our covariance matrix for the features, and this vector SXY is the cross covariance between features and targets, and then we have the sample means. So here we have an interpretable solution for the RSS minimizing weights, beta, and that can help us understand better what's going on in terms of our data statistics. All right, so that's where we left off last time. So today we're going to talk a little bit about Python, simple versus multiple linear regression, and some important feature transformations that we need to do, especially when we work with something called categorical data. Okay, so let's talk first about how we can implement this least squares solution in Python. So again, one option is to use NumPy. NumPy is like the numerical computing language within, or package within Python. And so it is possible to compute this beta least squares using this equation. It's not the best method, as I'll talk about, but if you wanted to do this, what you would do is you would first need to create this column vector of ones. And so here we're creating a matrix of nsamp rows and one column. And then we're using this horizontal stack command to stack that to the left of our X matrix and calling that the A matrix. So one thing that I should maybe just briefly mention here, if you're used to working with MATLAB, one thing that's a little bit different in Python is that in MATLAB, all the quantities are matrices, in that if you specify a column vector in MATLAB, it really thinks about it as a matrix with one column, or if you specify a row vector in MATLAB, it thinks about that as a matrix with one row. Python is a little different. If you just say, make a ones vector that's nsamp long, it actually makes a one-dimensional quantity that cannot really be compared to a matrix like this, which is a two-dimensional quantity. They're just simply different things in Python. So it's sort of important in some cases, like here, to explicitly make this a two-dimensional quantity that has one column, because that is treated as differently than a one-dimensional quantity. Like in NumPy, one-dimensional quantity, you can't really think about it as a row vector or a column vector, because there's no such thing as rows or columns when you're working in one dimension, if that makes sense. It's just like a list of numbers. That's kind of what it is. So like in this case, if you tried this without this comma 1, it wouldn't really work because it would give you some error like the dimensions of those two things are incompatible. But so by making this explicitly a column vector, we're able to concatenate it in this way next to x, which has the same number of rows as this one's vector. So does that make sense, what I'm saying? All right. And we'll see this later throughout the course, how we in some cases need to take one-dimensional vectors and sort of extend them to two-dimensional matrices in order to get them to work with, to get them to work in certain scenarios. Okay, so now that we've constructed this matrix A, there's several things we can do. One thing is you could actually do this chain of commands. You could transpose A and multiply it with Y. You could also make a new matrix, A transpose A, and you could explicitly invert that new matrix. You could do all that. But one thing that's important to note is explicitly computing this matrix inverse is not a smart approach, especially when the matrix gets large. This is because computationally, to compute a matrix inverse, the cost is approximately cubic in the dimensions of the matrix. Whereas if we do this a smart way, the computational cost will be quadratic. And that smart way is to attack this least squares problem directly using some numerical linear algebra routines, which are from this LePac library. And in particular, we want to use this least squares, LSTSQ, least squares command, which will run an algorithm that's more efficient than this to solve this problem. So this least squares problem shows up a lot, in many fields, and that's why there's specific algorithms. A lot of emphasis over many decades has been put on how do we do this efficiently. And so this least squares routine is doing this in a really smart way. And especially if you're working with large matrices A, high-dimensional matrices, you would see that this is going to be quite a bit faster than this approach here. Okay, so anyway, so if you're going to use NumPy, the recommended way to approach this problem is not to use this explicit formula, but just to think about it as a least squares problem, and then to use the least squares command, where you just give it the matrix, the vector of known quantities, A and Y, and then it will solve for the betas in a numerically robust and fast way. Okay, so that's certainly one way to do it. Any questions on this way? Yeah.
So those are like equivalent?
Yeah, so they're equivalent up to numerical precision, I would say. So like there could be cases where if you give this like a matrix where this is not invertible, maybe this would just throw an error, say I can't do that because the matrix, the inverse doesn't exist. Whereas even when that inverse doesn't exist, there often is a way of computing a least squares solution, and this will find it, whereas this could give you errors. And if the matrix is like very close to not being invertible, you actually could see some numerical errors that are amplified by this inverse that would not be amplified here. Okay. But yeah, if numerical precision wasn't an issue, these two things should be the same, at least when this is invertible. Okay, any other questions? Okay, so there's another way to do this, which actually, for our purposes, is going to be better because it's going to be consistent with a lot of other approaches we can and will use throughout the semester. And this is to use the Scikit-Learn library. That's the machine learning library in Python. And in Scikit-Learn, you basically say, this is a linear regression problem, so I'm going to use some linear regression methodology. And this methodology, we'll see, this is going to be the same if I do linear regression or linear classification or a whole bunch of other methods that we'll learn later. It all works the same way. So this is once you get used to this, it becomes very natural to do everything in this framework. And so it goes like this. The very first step is you instantiate this object, which is sort of It's a holder that knows about algorithms, that knows about data. You instantiate it just by saying linear model dot linear regression. And so that initializes a whole bunch of stuff inside that object. But so far, you haven't even given it any data, so it hasn't really done anything yet. So the first step after that is to give it the data and say fit. And when you run this command, it's going to essentially solve this least squares problem internally, store the beta coefficients internally, and not really report anything more than that. If you want to get access to the beta coefficients, you can do this using another extension. I think it's param underbar that will print out the beta coefficients. If you want it, that actually prints out beta 1 through beta d. If you wanted to get the intercept, that's a separate command. I think it's regression.intercept. But finally, we don't really care necessarily what the coefficients are. We actually want to use them to, for prediction. So that's another thing you can do. You can say regression.predict, where it will take the internally stored beta coefficients, apply them to these features x, and generate the linear predictions y corresponding to those features x. So that's what we're doing here. X is our training data. So y predict will be our y hats. Okay, this is like our y hat vector, which is a vector of all the predictions of the training labels. And then you can see that we can compute RSS just by taking y predict minus y. That will create the difference of the what we call epsilons, the residuals. We're going to, this star star 2 will square every entry in that vector, and then we will sum across that vector to finally get our RSS. Okay. And then if we want to compute R squared coefficient of determination, we know that you can do this by taking RSS, dividing by the number of training samples, and dividing by the variance of y. Here we're doing this by computing the standard deviation and squaring it, but we've seen other ways to do that to get the variance of y. In any case, once we've done this, we can print out the R squared. And for this particular model, this is a diabetes model where we're trying to predict the disease based on various like biometrics. We find that we get an R squared of 0.51. So what does that tell us about this linear fit? Good or bad or?
Reasonable. It's okay.
Okay, I would say okay. If it's close to 1, it's good. If it's close to 0, it's bad. If it's in the middle, it's okay. It's not great. All right, but it is what it is. Some data sets, some machine learning problems are easy in terms of the data. Some are just hard. No matter what you do, it's just actually impossible to do very well. That's just because the data may be very noisy, very inconsistent, and so on. So that's just what we have. And it could be that maybe if we apply some more sophisticated model that's nonlinear, we could do much better. That's definitely a possibility. But in any case, we know how good our linear fit is. Okay, so any questions so far on how we've implemented linear regression?
So
Yeah.
what's the difference between the first instruction regression.fit and the RSS that we're calculating?
So this is, in this step, it computes the beta least squares vector. So internally, it computes it and stores it. This step is nothing more than A times the beta hat stored. Right? And so and actually it's, maybe I should be a little more explicit here, because there's like a column vector of 1s, and then there's whatever you put in there. So if you put in some new vector x that was not used in training, it will do the prediction on those new features. This just happens to be, this x matrix happens to be our training data. Okay. But the prediction method works for any data you give it. It doesn't have to be your training data. Okay. All right. Any other questions on this implementation? Yeah?
Is there a closed form for like R squared, just like in the one-dimensional case we did?
Yeah, that's a great question. Yes, there is a way to write r squared in terms of these quantities. Maybe it could show up, as a homework problem or a test problem or something. It's not very difficult to derive. But yeah. Yeah, it's not in the notes, but it's not difficult to derive, and it's a great question. Okay, great. Any other questions? Okay, good. So we learned how to implement it. So now let's kind of come back and think a little bit more about what we've done and play with our data a bit more. So just to put things in perspective, in Unit 1, we worked on simple linear regression. And in that case, there was one feature or predictor that was a scalar. And so our model was like this. And so in this unit, we did multiple linear regression. So now we have multiple features or predictors. We have a more complicated linear model, although it's still linear. And these two become equivalent in the case that D is 1, in which case all this stuff goes away. So then one might ask, is there an advantage to multiple linear regression over simple linear regression? Or what do you guys think? If we have this diabetes data set, right? We could have tried to predict the target based on any one of our features, but actually what we did most recently is we predicted it based on all of them. So what do you think? Is this always going to work better?
It depends on the relationship between the features.
Okay.
Might be the output is dependent not only on one feature but all of them. Like we get the result from when we combine all of the features.
Yeah, so do you think it's going to be better then when you use all the features?
I think.
Okay, how many? This is actually not a easy question, so don't feel bad. How many people think it will be better, always better to use all the features? Raise your hands. Okay, how many people what? Okay, we got a brave one. And how many people think it will not be better to use all the features? We should. There's cases where we don't want to use all of them. How many people think? Okay, and how many people don't know or don't care? Okay, so what's actually a key thing that we've been a little bit vague about is better in what sense? So let me try to clarify this. If I ask you, based on training data performance, RSS on the training data, is it going to be better to use all the features or maybe not? How many people think yes, use all the features? Okay. And some people think maybe not? Okay. It turns out that, yeah, if we're looking at the training data, we definitely want to use, if we care only about performance on the training data, we want to use all the features for our prediction. Okay. But the reason why that's a little bit tricky is that, as we'll learn in the next units, in the next 2 units, when we don't care just about what happens on our training data, but on some unseen data, we can call that test data, that we're going to get later after we're done training, when you care about that, then it's important, in some cases, not to use all your features, because some of those features could be confusing your estimator more than they are helping it. But if all you care about is the training data, yes, you definitely want to use all your features. So the brave ones won out in this case. But let's see this a little bit more. So this is the diabetes demo. And what we've done in this little piece of code is we've just gone through all of the 10 features one at a time to see whether, how good that feature is for prediction of the target. And we printed out the 2 beta coefficients, in this case using feature j equals 0 or j equals 1 and so on, as well as the r squared that you get. And so when we look through the r squareds, we see some values that are extremely low, like 0.0018, right? So that would be like, that feature is almost useless in terms of prediction. We see a few better ones. I think the best one is this one, right? 0.34. But remember that when we did multiple linear regression, we got all the way up to 0.51. So we definitely see a gain in going from single features to all of them. But if you basically redid this experiment where you looked at all possible combinations of features, you would see the same behavior, that it's never a bad thing to use all of them, because the least squares predictor, if there's some feature that is, totally useless for prediction, maybe it's just random noise, the least squares predictor is smart enough to know to assign a beta hat of 0 to that. It will figure that out. But if you don't let the least squares predictor do its magic and you only show it like some subset of features and some other subset, then there's no way that it could use the information from the ones you are leaving out. That's a little bit of the intuition about why it's better to use all the features, because it gives the predictor more freedom. And in this case, the predictor is able to mathematically exactly minimize the least squares training data. Least squares RSS, right? Sorry. Exactly minimize the RSS on the training data. That's what the least squares solution is. So it has exactly the right objective. It's able to minimize that objective perfectly. So you should just give it all the information that you have and let it do its good work. Okay. So are there any questions on this idea or any doubts? Yeah.
So with multiple linear regression, are you just getting one regression line from a bunch of different features? Is that like the output?
So we saw a picture of this in 2 dimensions. This is what I would say is the picture that you should be thinking of. So we get a plane, or hyperplane. The hyperplane is of dimension d. In this particular case, this is an illustration where d equals 2. So we have x1 and x2. But more generally, there's this d-dimensional plane that we move around to fit our data and use for prediction. When we do linear prediction, essentially we're just fitting a line, one axis at a time, and we can't use the joint information, can't use the information from all the features simultaneously. Okay, any other questions about why we want to use all the features if we care about training RSS? Okay, so but now let's start to talk about things that are a little bit more practical in machine learning, which is the fact that you have a certain data that you use for training, but then when you actually apply this in the real world, you're going to be applying it on data that you never saw for training. And you have to be aware of that fact, and that ends up being one of the largest challenges in machine learning, is training such that the performance later in the real world is good. That's called generalization. Does your model generalize to data beyond that for which it was trained? So just as the very first step, let's talk about doing this by taking, if someone gives us a data set, that's all we have to work with, like this diabetes data set. We're going to simulate the real world by partitioning this data set into 2 pieces. One we'll call the training data. We'll use that for training. The other part, we'll call that the test data, and we will not use that for training, but we will use that to evaluate how well our trained model is working. Okay, so in this case, just for this experiment, we're going to use 300 of our 442 samples for our training data, and then we're going to use the rest, 142 samples, for our test data. And here you can see how we did this in the code. We set 300 for NSTrain. NSTest is the total number, which is 442 minus NSTrain. And then we take our total, this is our feature matrix X, which contains all our data. But instead of using all the rows, we're going to use row 0 down to row NSTrain. Okay, so the way that indexing works in Python, another thing too, if you're coming from MATLAB always starts indexing at 1, whereas Python starts at 0. And it's a little confusing because when you do this, it's going to take the indices from 0 up to NSTrain minus 1. And that way it's going to give you a total of NS train indices. Okay, so that's what it's doing. So that's going to be our training X. Our training Y is also going to contain the first NS train rows of this Y column vector. And then X test is going to start at NS train and go to the end. That's what the colon with nothing after it means. And then this colon, just like in MATLAB, means use all the columns. Okay, so this is how we split into training and test quantities. And then you can see this is our machine learning method using Scikitlearn. We fit our regression object on the training data. We then can predict on either the training or the test data. So these are our training predictions, these are our test predictions. And we can then compute R squared on the training and test sets. And in this case, things worked out pretty well. You can see that this is similar to the number we saw before. It's not exactly the same because our training data is 300 samples, whereas before it was 442. So, but it's still pretty close. And our test data, our test RSS, is pretty close as well to the training and to what we had before. What you tend to see is that the test RSS usually is a little bit lower. Or, sorry, test R squared is usually a bit worse, a bit lower than the training. Because the model cannot, the model is really minimizing. There's no other model that could get you an R squared. There's no other betas that get you an R squared on the training that's lower than this. It's impossible. But, there could be other models that could work better on this test data. In fact, if you use the test data for training and then you computed the R squared that way, it would be lower than this value. Okay. But in any case, you're never really sure what's going to happen on the test data. You just hope that it's similar to your training data, but sometimes in practice it could be very different, and that's a bummer, and you have to try to find some ways around that. Okay, we're gonna discuss this test train stuff a lot more in the next unit, but it's something just to talk about a little bit now. Okay, any questions on? Yeah.
Can you re-explain the indexing again on the X train using the NS train? So the colon to NS train.
Yeah. So
0 to basically 299, right?
That's right. That's right. Yes. This is. This guy is going to be 0 to 299. Well, again, I shouldn't write it that way. I should write 0 to 299. And that's going to be 300 numbers. And then this is going to be 300 to the end, which happens to be 442. Or I guess 441 is 441 in NumPy indexing because NumPy starts at 0. So when there's 442 samples, 441 is the index of the last sample.
I guess maybe where I'm confused is because you say at the top statement that NS train is 300. So where did you get the 442?
Oh, the total is 442. We just saw that earlier in the.
Okay.
Yeah. So this, yeah. So total N is 442 in this data set. Okay. Does that clarify? Okay, great. All right. Any other questions on anything here? Okay. So now let's talk about a very important topic, which is what happens when you get features that are not numbers. So these are officially called categorical variables, and they're variables that are categories, not things that you can think of as ordered from small to big. So as an example, maybe we want to predict the miles per gallon Y of a car given horsepower X1, brand X2, and the brands we're working with might be Ford, Honda, BMW, right? So these brands are not things that we can order in a generic way. We can't say like Ford is always less than Honda is always less than BMW. So it doesn't make sense for us to assign numbers like 1, 2, and 3 to these quantities and then to to proceed with our linear modeling because that when you do that, that presumes some ordering between those quantities, and there is no ordering, right? So we have to use a different approach. So the approach we're going to use is called one-hot coding, and essentially what we do is we code these quantities as binary vectors. So here's an example. So for x2, I'm just going to notationally expand that into x2 sup 1, x2 sup 2, and x2 sup 3. But it's just trying to say, like, these are all related to the x2 variable, but they're actually now 3 different new variables. And this is how we could do the coding. Ford is 100, Honda is 010, and BMW is 001. Whichever one, like, you could reorder these. It doesn't matter which one. But the point is, you can see they're all different than each other, but they're all very similar, right? They're all just a binary vector. So they all get treated. They get treated in a way that is not forcing and ordering among them, but it is numerical. It's something we can work with in, linear regression. So any questions on how we're doing this? Good? Okay. Now let's try to understand what is actually happening when we do this. So the new linear model, so essentially this brand x2 has now been expanded into x21, x22, and x23. And each one of those is going to get its own regression coefficient. And if you think about what's happening, when you look at the subset of data that are the Ford samples, all of those samples are going to be using this model with the beta 2 here, because for all the Ford samples, this is 1, this is 0, and this is 0. Right? So effectively, these terms go away, and you just have the first 3, but actually x2 goes away as well, and so you get this. Right? That's going to be the model that you apply to all your Ford samples. When you look at all your Honda samples, this goes away, and this turns into a 1. So your Honda samples are basically getting this model. Similarly, the BMW samples are getting this model. So now that you see that, you can actually understand what is happening when you apply this coding scheme. Essentially what it's doing is it's allowing a different intercept for those 3 data types. Right? Ford is going to have the intercept beta 0 plus beta 2, which can be different than Honda's intercept of beta 0 plus beta 3, or BMW's intercept of beta 0 plus beta 4. Of course, all these numbers, all these betas will be fit using the training data. So they will take on some value when you're done training. But you can see that, for example, Ford is getting the same slope. All the Ford samples are getting the same slope beta 1 as all the Honda samples and all the BMW samples. So this form of one-hot coding, sometimes we call this one-hot coding the intercept, because that's all it's doing, is it's making a category-dependent intercept. Okay. Any questions? Yeah.
Why do you use all the data together for for getting 3 models? Why not just isolate each Ford, Honda, BMW, and then get beta 0, beta 1 for each?
Yeah, that is certainly an option. So we could basically use a separate beta 0 and beta 1 for all those samples. So you could say that when you do machine learning, you're sort of trying to use all your data and exploit similarities in all your data if you believe those similarities exist. So like when we do our linear regression, we're fitting one line to all our data because we are kind of assuming or believing that one line is enough to fit all our data. If we split our data into 2 parts and use different lines in each part, if we have some reason to believe that that's better, like maybe some knowledge of the physics, then that could be an appropriate thing. But otherwise, what you would find, and we'll see this a bit later, is that you will actually, as your data set shrinks, there's more variability in your model, there's more noise, and you'll get a worse prediction. So that's why in machine learning we like big data sets, because more data means less variability in the end. But that's a very good point, because there are times like here where you would say, and in fact that's the next page, if you maybe know something about the problem you're solving, like what if you suspect that different brands use different methods to measure horsepower, and you believe, like, those BMW guys, they cheat. They always report this big horsepower, but it's just because they have this weird way of measuring it, and I know it's not the same way that the Japanese engineers at Honda measure it, and therefore we can't use the same betas for both of them. We're going to use different betas for each. But then you might say that I actually believe that all the intercept terms, those should be the same. So it's possible to do that, and if you want to do that, here's how you can do it. You use the coding in the same way, but then you build the model in a different way. You can see that beta 0 term is common, but now these are like binary switches that are either on or off, and only one of these three terms is going to be on at a time. So then you'll get these models, and in some cases that might be a better thing to do. So yeah, so this we could call one-hot coding on the slope, and if you do them simultaneously, then you're essentially using completely separate models for each manufacturer, and maybe that's justified. Maybe that's what you should be doing, or maybe you can get some advantage of pooling the data across them. It's hard to say. Okay, so is this one-hot coding stuff making sense? Okay, now there is one issue. Let's return to the one-hot coding, the intercept, which was the first thing we looked at. And this is where we have this coding, and this is what we did with that coding. So the trouble here, maybe, does anybody see, let's just go back here. Does anybody see kind of something that bothers them about what we're doing here? Something that's a little bit weird? So we're
You have two constants.
yeah. So we have two constants, but maybe another way is, like, how many intercepts are there in this problem? 3, right? There's one separate intercept for each class. And how many variables are we using to parameterize our intercepts? 4, right? Beta 0, 2, 3, 4. So we have 3 degrees of freedom, but 4 variables are used to model the 3 degrees. So there's a redundancy. And that redundancy can cause problems, especially when we try to fit our data. In particular, it will make this matrix non-invertible. So let's try to convince us of why that is. So, okay, sorry, it looks like the notation, no, everything's good here. So this is the beta vector with the 1, 2, 3, 4, 5 terms. And let's imagine what the rows of our A matrix will look like. So, okay, whenever we have a forward sample, the row of A matrix will look like this, right? Because the A matrix always has a column of 1s on the left. Then the second column will be the feature data. That's the horsepower. And then the rightmost 3 columns for all my Ford samples will be 1, 0, 0. Similarly, for all the Honda samples, these will look similar, but then they will be 0, 1, 0, and then for the BMW, it will be 0, 0, 1. Okay, so now, if I'm clever, I can come up with this particular beta vector, which happens to be minus 1, 0, 1, 1, 1, that if you notice, when I multiply A by that beta vector, I get A times beta equals 0, right? Because no matter what the value of X is, I'm going to zero that out when I take the inner product of this and this. So I'm going to zero that out, and then this times this plus this times this will give me 0, and then these will also give zeros. So hopefully you can see that when you take the inner product of this beta and every row of A, you will get 0. So if this holds true, then that means that I can multiply both sides of this equation by A transpose, and this must hold true. And now coming back to linear algebra, if there's some matrix, in this case the matrix is A transpose A, for which when you multiply that matrix by a non-zero vector and you get 0, that means the matrix is not invertible. Maybe one way to think about that is if you think about the matrix as a system and think about beta as a signal going into that system, what's happening here is you're putting in a non-zero signal into the system, and the system is killing it. It's turning it to 0. So that if you wanted to go backwards through that system and figure out what did you put in, it's impossible, right? Because you got 0 out, there's no way to figure out what happened to the input. Like, no matter how beta is scaled, if I double beta, it's 0. So I've certainly lost that. So that kind of gives you an intuition about why these matrices are non-invertible. Whenever the matrix has this property, there exists non-zero vector such that multiplying that matrix by that non-zero vector gives you 0. You know that this is non-invertible or otherwise singular. Singular is just another word for non-invertible. Okay, so here we see the problem, but there's a simple solution. The solution is just to omit that last variable and do your coding this way. And when you do the coding this way, essentially, you just get rid of this. And now you have 3 variables for 3 intercept terms, and you don't have that problem anymore. Okay, so it's just like a little thing that you can do, an easy fix to the problem. The same applies if you have 2 categories. If I have 2 categories, I would start out by doing this, right? But then I would have the same problem with the non-invertibility, and I would want to get rid of this and do my one-hot coding with a single number, which is 0 or 1. Okay, so it's always you go however many categories you have, you go one less one-hot coding possibilities in this scheme. Any questions?
Can't we remove beta 0?
Can you remove which?
Beta 0.
Yeah, that is certainly another possibility. Another possibility. So in some cases, let's see. So, like if you're using Scikitlearn, it will automatically fit an intercept term unless you tell it not to. So it's just like it requires a little bit of a different data flow. You would be adding one more feature and then you'd be turning off the intercept. So yes, it would work. Okay, so there's another way to solve this problem that we'll learn about in Unit 4 is under some conditions you can handle non-invertibility in this. And one of those conditions is when you add regularization. And in that case, that could also get around the problem. But for now, this is the simplest approach, is just to get rid of some of this redundancy that you're adding through this coding scheme. Okay, so that's all I have to say about the one-hot coding. Are there any questions on anything? Yes?
I just wanted to understand, is the problem of singularity, that's only in the very, it's not guaranteed. It's only in the case that your beta 0 ends up being -1 and that your other coefficient ends up being beta 1, 2, and
I see. No. So
is it guaranteed?
So this is like if there exists any vector beta that's non-zero, where you get this, if you can find 1, then this must be non-invertible. So it's not that the problem only exists for this particular beta. You could say that the problem exists, there's a whole subspace. So like in this high dimensional space, there's going to be a subspace along which you cannot get back data when you put it through. And so it could be that, there's important stuff in that subspace for all these problems you're working on. And that subspace will always be, you'll never be able to recover that. Yeah. And more than that, like if you tried to actually do a matrix inverse, you'd get some error. It would say it's impossible, I can't do that. Was there another question?
terms of the like different categories, if you were to add an additional category, you would have to add another
Yeah.
row. You wouldn't be able to do like 1-1.
You'd add, yeah, every new category means your one-hot coding has one more dimension.
Okay.
Yeah, so it's adding another column, right. And was there a question over there? Yeah.
What would happen like two rows of A are very close to each other?
Yeah,
For
so
example.
there's other reasons, so there's kind of, there's various reasons why you could get this singularity problem.
Yeah.
So here what I'm saying is no matter what your data is, let's say you have lots of data and then you're adding this one hot coding, then this will definitely be singular. But another problem we saw before is if you don't have enough data, if the A matrix is a wide matrix, then that alone, if it's wide, I don't know if you can kind of visualize, a wide times a tall, this gives you a matrix that's not full rank. This is also going to be non-invertible. So this is a case where we like to have at least as many data samples as we do features, plus one because of the intercept. But even then, we're not guaranteed to have invertible because it could be that, let's say, two of our data samples are somehow, or maybe some set of them are not linearly independent, they're redundant. In that case, we also have non-invertibility. Usually that stuff doesn't happen, especially when we have lots and lots of data. But I guess there is the chance. It just rarely happens. Okay, great. Any other questions? All right. So, okay, the very last thing to talk about today is sort of another way we could transform our features. And so let's say that we just have a single variable x, but we would like to do polynomial regression. We want to do a polynomial model. So in that case, what we're saying is we want to do something like this. So here we have the intercept term as always, the linear term is like always, but now this second term we actually have x squared, and the next one x cubed, and so on all the way to x to the power d. Okay, so this is definitely a useful thing we might want to do. The first point is we have all the tools to do this, right? Linear regression works fine for this in the sense that all we have to do is define feature x sub j as x to the power j. And so it's like we've taken our single x and we've created d different features just by taking it to different powers. So that means we can go ahead and use all the stuff that we did previously in this unit, and it works. So that's great news, right? So like this whole idea about like linear models being so limiting is actually, you can do a lot with linear models as long as you do allow some pre-processing, nonlinear pre-processing, as we've done here. And you can imagine there's all sorts of other things you could do. Like if I had two x's, I could have all these different cross polynomials. You could imagine coming up with tons and tons of new features. We'll see that there's actually a problem with that in the next unit, but for now, sounds like a great idea. And it's not just with polynomial powers. Like, you could create other features nonlinearly, like in this case, cosine omega jx, where the omega j's are different omega j's. This is like, different frequencies you could use. So there's all sorts of ways you could take features and do some sort of nonlinear function to them to get a new feature and then do linear regression with that. Okay. So if you think about what is the linear in linear regression, it's that it must be linear in the betas, not the x's, the betas. Because as soon as you put squares on the betas, then everything falls apart. Then all the derivations we did, we were taking gradients with respect to beta and setting them to 0, no longer works. Okay, so it's fine to have transformations of the x's, but it's not fine. The betas, y must be linear in the betas. That's what we really need for linear regression to work. Okay, so all right, so that's really kind of the last message is tons of flexibility in terms of sophisticated pre-processing of features, but you just have to have the betas be linear, and then you can do this closed form least squares fitting that we've done in this unit. Okay, any questions on that? All right, so, but there is kind of an important concept that we've uncovered here, maybe accidentally. So if you want to do this, how should you pick D? Because now it's a choice, right? Unless some domain expert tells you, no, this is a quadratic model. In general, you're just given a bunch of data, and you're saying, I'm not that happy with a linear model. I want to do more, so I'm going to consider polynomial models, but how far do you go? So here you can see some raw data. Just visually, it looks like this ninth order polynomial fit is the best, but is it always that higher powers are better? What do you think? No. But again, we have to be careful. Better how? So what if all I care about is fitting my training data?
That would be amazing.
Is there any reason not to use a very high power model?
No.
No, right? Computationally, maybe you can get into trouble eventually, but no. But when you care about this thing working well on test data, yeah, then it's a problem. It's something called overfitting, and that's actually what we're going to talk about in the next unit. That's exactly the concept of the next unit. Unit 3, let's see. I need to load it here. Okay, so we just have a few minutes. Can't get very far, but let me start with it. So so basically, we're talking about polynomial regression, just like we left off. That's what we're going to focus on for this unit because it's a nice example of the main topic, which we want to talk about, which is called model selection. And so in polynomial regression, we start with a scalar x, but then we expand it into multiple features by taking different powers of x all the way up to the dth power. Okay, so polynomial regression, D is going to be the degree of the polynomial in our model. And once we fix D, we can fit our model, no problem. But the main question for this unit is, how do you choose D? That's modeler selection. So what we're going to do in this unit, the data set we're going to play with is not actually going to be a real data set, it's going to be a synthetic data set. And what's nice about synthetic data is that when we create it, we can control it, we know the truth, we can compare how well predictions work relative to the truth. It's very convenient. So that's what we're going to use in this unit. And the way we're going to generate our data is we are going to say yi is going to be some polynomial function f of xi plus some noise epsilon I that we're going to add, and we're going to generate that noise random data. It's going to be from a Gaussian distribution with, so this is Gaussian whenever you see the script n, Gaussian distribution with zero mean and variance sigma squared. The value sigma squared is, it looks like the standard deviation is 0.4 when we generated it, but it's just some number. And as you can see, this is the result. If there was no noise, all the data would fit exactly on this curve. It turns out that the true model from which we're generating our data happens to be a cubic polynomial. So this is the true one. Okay, but we don't necessarily know the true model when we work with data. We're trying to figure out what is the right choice for the model order D. So anyway, this is what it looks like. We're actually generating the x values also randomly. You can see they're uniformly distributed between 1 and -1. And there's 100 of them. So 100, our data set is of size 100. Okay. So let's first see what happens if somehow a genie tells us that the true model order is 3. And this is the result of doing the fit. So the true curve is red, the predicted curve is green, and you can see that's really pretty good. They almost look identical. Okay, so works really well. We have enough data at least to make it work well. So a little bit of detail about how did we actually do the fitting. So in the last unit, we learned about this linear model linear regression that we could use in Scikit-Learn, and that's definitely an option. If you want to take that option, you would need to take your original data, x, in this case, which are these values, and you would need to create a new data set where you expand it into however many features you need for D and so on. That's definitely a possibility. We're going to do something just a little bit different. We're going to use the NumPy polynomial package, which is kind of a shortcut. And the polynomial package has a bunch of nice routines. So for example, this polyfit routine does least squares fitting of the polynomial coefficients. That's what it's doing under the hood. So we're just going to give it the x data, the y data, and the model order D, and it gives us the beta hats. And then we do polyval in order to apply those betas to some new feature vector xp. So that's basically how we drew this curve. We essentially made a vector of, so xp is just like a grid of 100 samples between 1 and -1, and we applied our polyval to those 100 samples. That gave us a bunch of samples, and we just connected the dots essentially with this, the plot command that connects the dots. So as you can see, everything looks really good. But if we would have chosen a model order like d equals 1, which is smaller than the true model, well, as we know, that's a linear model, right? That gives us this green curve. As you can see, it's not as good of a fit. Or if we choose a large model order like d equals 15, then you get this green curve, which, as you can see, is kind of a strange fit. And in particular, it's sort of going nuts over here, which is a region where we don't actually have any training data. Okay. But just because we don't have training data there doesn't mean we won't have test data there. Maybe someone asks us to do a prediction of this, and if the red one is our true polynomial model, we're going to be way off, right? This is going to be at some incredibly high number. So it's going to give us a terrible fit. Okay. So more generally, here's kind of like another just nice illustration of what can happen. So when the model you use is too weak, it's not complex enough, we call that underfitting. When the model you use is too strong relative to the true trend, you call that overfitting. And here's an example of what can happen with overfitting. It could be, if the data allowed it, and your model order D was high enough, that you actually come up with a curve that goes perfectly through, okay, here it's missing this one, but it goes perfectly through all your training points. It gives you exactly 0 prediction error, which sounds great until, there's a test sample that's maybe over here, and you can see that's not going to be sitting on the curve from the training points. So you can kind of see why, if you care about training data, there's no problem, but if you care about test data, then this thing called overfitting can happen. Okay. So that's a good place to stop. Next time we'll talk about how can we solve this problem, how can we choose D, but we'll do that on Monday. So have a great weekend.